So in this lesson, we're going to revisit the formulas for center of mass and moment of inertia and try to see if there's a way we could use integration to figure out these values as well. So if I look at moment of inertia I, if I had a series of, or a set of point masses, the way to do I would be to take I is equal to the sum of mr squared for all the individual masses. Well, if I have a distribution of mass, whether it's uniform or not uniform, I could say that this is the integral of r times dm, where dm is the mass of each little individual chunk of this object, and r, of course, is the distance it is away from your axis of rotation. Basically, it's like doing mr squared, but doing it for every little chunk, what I call dm in here. For center of mass, the way I could rewrite this, the normal way I'd write it is 1 over m times the sum of all the masses times their positions, m times x. Well, if I rewrite this a little bit, instead of having m times x, where m is the mass of each little point or each little particle, I'm going to say dm is the mass of a tiny little part of this object, and so I do x times dm. So to use dm, what I'm really saying is I'm breaking this solid object into tiny little particles, and dm is the mass of each tiny little particle. So I think the most challenging thing of what we're going to do here is setting up what these integrals actually look like, figuring out what the functions actually look like that we'll use in order to do some math. So let's go back to moment of inertia, and let's take a rod with a mass m and a length L and rotate it about one end and try to figure out what is the moment of inertia using integration. Now this is one that we could go look it up in the book, and we know it should be 1/3 ml squared. That's what it is. But let's use integration to show that's true. And so moment of inertia is the integral of r squared times dm. So the way I would define dm, or I need to figure out what dm is dm is the mass of a little chunk of this rod. I've put it in red there. So dm is the mass of that red chunk. And then r is that length. The thickness of one of these red chunks I'm going to define as dr. And so what I could say about dm is that it's equal to lambda, the density of the rod, times dr. Well, if this is a uniform rod, lambda is easy to find, just mass divided by length. So lambda basically talks about what is the mass per unit of length. Dr is what is this small little unit of length. Dm is how much mass is this small of a unit of mass. Well, if I plug that in to my equation and make it a definite integral, the value of r can range from 0, that's all the way back at the axis of rotation, all the way to L, the end of the rod. And so I'd say I is equal to the integral from 0 to L of r squared m over L dr. And if I rearrange this, the m over L flies out of there, and we get m over L, integral from 0 to L, r squared dr. Well, if I do that integral 0 to L, r squared dr, I get r cubed over 3 evaluated from 0 to L. When I evaluate that from 0 to L, I get L cubed over 3 minus 0 cubed over 3. So I have M over L times L cubed over 3, essentially. And what you end up with is 1/3 ml squared. That's what the moment of inertia of a rod is. And that actually verifies what we already know about that rod. Now, it's worth pointing out this would only work if this is a uniform rod. But let's throw something in there to make it a little more fun and a little more challenging. And let's say we want to calculate the moment of inertia of a rod with length L that is not uniform. So the mass distribution is not uniform, but the distribution of mass is known as a function lambda times r equals 2m over L squared r, where r is the distance from the axis of rotation. So essentially what this looks like is that the further away from the axis of rotation you get, the bigger the mass actually gets of the rod. So this is a rod that at the middle essentially has no mass, but has lots of mass toward the outside, and so the mass increases linearly as you go out of the rod. So let's start the same function. I equals the square, or the integral of r squared dm. Still need to find dm. Dm still looks the same. It's got to be lambda dr. But in this case, I actually know a function for lambda that I can plug in there, that it's 2m over L squared r. So if I plug that in there, what I end up with is the integral from 0 to L r squared times 2m over L squared r dr. The 2m over L squared is just all a constant. It can be pulled out. If I integrate that, it looks like I get an r to the 4th over 4. Well, if I substitute L and 0 in there, I end up with 1/2 ml squared. So by making this a rod where the distribution of mass increases as r increases, we've increased the value of I. And we increased it by, well, about 1/6, really. Or 1/6 ml squared, I guess, would be the best way to say that. So let's do center of mass. Let's say we wanted to calculate the location of center of mass for a uniform beam of mass m and length L. Now, I'm going to say the distance x equals 0 is the far left end of the beam. The nice thing about this is that if it's a uniform beam, I know that the center of mass has to be at L over 2, correct? So we're going to do the same defining things. I'm going to say center of mass is 1 over m times the integral 0 to m x dm. I still need to define dm. I'm defining dm the same way. Dm is lambda dx, same thing that I just had. This uniform beam, lambda is m over L. And so I can plug that in. And so I get 1 over m integral from 0 to L x m over L dx. Now let's pull all that out. The m's cancel. So I get 1 over L integral 0 to L x dx. If I integrate that, I would get 1 over L times L squared over 2, which sure enough verifies that the center of mass is at L over 2. So guess what? My equation works pretty well. So it works pretty well to calculate the center of mass of this uniform beam. I can also calculate the center of mass of my non-uniform beam too. All that I would do is at this point here, instead of putting m over L in, I would just plug whatever the function for lambda is in there. In this case, the lambda would be 2ml squared over x. And so I would plug that in at this point, 2ml squared over x. And you could actually then work it out if you wanted to. Looks like it might be kind of fun to do that as well. What we'll do in class is we'll talk about the disk and the ring and kind of how the disk and the ring work. I like to do those in class because I actually have some manipulatives that we can use and play around with. We can also talk about things like a uniform sheet or other types of distributions of mass and try to figure out center of mass, moment of inertia for those types of shapes as well. So that'll be kind of the end of this lesson. We'll take a look at gravity inside the Earth as our next lesson. I just wanted to check to see if I wanted to put that in lesson 31 or lesson 32. Looks like it's lesson 32.